With this, let me take an example for the link prediction. Here I will look at East protein interactome as my example. I have around 6,526 proteins, and we have around 4 lakhs interaction, to be precise 3,99,550 interaction between different protein. Now the question is, I want to predict a link between proteins given the node embedding, or in general given the nodes. Here the link prediction problem is formulated as binary classification problem, where 0 means no edge. In other words, there is no link between the given pair of nodes or given pair of node embedding, or there is a link if the output is 1. It means there is an edge present between two given pair of nodes. And here for node embedding we can use any node embedding techniques which we have used in the node embedding lectures. Now let's look at the embedding size. Again the same questions we are asking. We are trying to actually use logistic regression as our classifier for determining the embedding size, which is embedding size of both D as well as D dash. Here I am assuming D equal to D dash, so the embedding size everywhere is the same. We are doing a randomly removed edges with the label 1 in our data sets, so we already have a training and test sets, so we can know how good we are doing in terms of embedding as well as later on in terms of classification. And also we have randomly sampled non-existing edges, label 0, so we have a very balanced data sets, equal proportion of labels with 0 and 1, and we are splitting it randomly. Now here if you look at it, we have used different kind of embedding size, 16, 32, 64, 128 to 56, and different kind of operator, which is average, hammered, L1 and L2, which is embedding operator for edges. And we can see that the average and on an average L1 provides us a better operator. Here L2 also performance is as good as L1, and if you look at it, after 32 the performance is not changing much. Here also performance is best for 64, but if you look at 32 size of embedding, it is not it's a marginal improvement, a negligible improvement in fact. Similarly for this one, and you can see the 30 for head hammered 32 is performing better, so we can choose 32 as the best embedding size. In fact, if you see that if we increase the embedding size in most of the operators for G, the performance is degrading, you can see, except for averaging where performance is more or less stagnant. So we'll use a embedding size of 32, and we can do the classification of model where we'll look at deep walk as our embedding techniques. Embedding size for edges will be 32. Again, same way we are actually performing the analysis for classification, ensuring that we have a balanced class, means equal proportion of both labels 0 and 1. We are not discussing imbalance class problems. There are cases where imbalance class problems are very natural to the problem, but currently for this particular simulations we have kept both of this class similar, and we are doing random split, and here are the results for 4 different classifiers. We have used logistic, decision tree, naive Bayes, and neural network to predict whether there is an edge between 2 nodes or not. For different embedding operators, we can see that the performance of average Hadamard L1 and L2, the neural network performs significantly well irrespective of embedding operator. Similarly, we can see that logistic classifier, logistic regression, performs better on an average in all of them, while decision tree and naive Bayes are not performing well. So we can say that best models which we have currently are logistic and neural network models for this particular data set. And average and Hadamard are providing a better operators when we look at the classification task, while for the embedding class task we did not get better performance with Hadamard in general. It was L1 and the average. So you have to look at different operators and see which operators provide you a better performance or better embedding of edge, and then we can use it. So we can use node embedding based techniques combined with edge operator G to create edge embedding and use that embedding G embedding to perform task which involves 2 nodes or 3 nodes, or in general link prediction task. So far whatever we have seen is a shallow embedding methods, and although they are quite versatile and provides us a decent results, there are certain limitations to the shallow embedding in general. One of the nature of the shallow embedding is they do not share the parameters. Typically, parameter sharing improves the efficiency of learning, and it also provides some kind of indirect regularization. It means that they are trying to find out a model with lesser and lesser parameters, or they are not, when we share the parameters, we have more parsimonious models. However, if we look at it, shallow embedding does not share parameters. In other words, for each node, we have more or less a unique number of parameters. We are having a lookup table. For each node, we have embedding. For U, we have a set of embedding set of values, which is the embedding vector. For V, we have, for each node in V, which is node set, we have individually embedding of dimension D. We do not share parameter between node U and V. So there is no sharing of parameter between nodes in encoder. And other problem, because of not sharing the parameters, when we try to perform shallow embedding on graphs and graph size increases, the number of parameters grows with it. And that's again an issue with a shallow embedding. And that's why it's a computationally and statistically inefficient when we do shallow embedding. Another problem with shallow embedding, if you recall, that we use node as an entity and create for each node using encoder and embedding. It does not leverage node features information, or even in the case of edge embedding, edge features also. Let's take a simple example of molecular graph. If you recall, in a molecular graph, we have different kind of atoms which are considered to be node, and the bonds, which can be different kind of bonds, different characteristic of bond, considered to be in the edge. So we have created a graph for each molecule. Now when we try to embed, we use only the position of node as it is. However, each molecule has its own atomic number, charge, bonds, orbital hybridization, etc. features. And those features play important role in creating an embedding which allows us to do property prediction and other tasks. However, we cannot leverage those features because shallow embedding techniques do not consider these features. Shallow embedding are inherently transductive in nature. What does it mean? When we perform training, we have a set of nodes. When we go for testing, we cannot generate an embedding for nodes that we have not seen during the training phase. In other words, we cannot create new embedding for a new node. And that actually is one of the largest limitation, because in many cases we'll have a new protein or a new disease and we do not have that disease earlier in our database. Then how can I actually create an embedding and perform tasks which may be node classification or a link prediction? Hence, the shallow embedding has these limitations, and that is why we will look at more generalized encoder-decoder approaches which can work on graph, or it is called famously graph neural networks, which can allow us to overcome several limitations of shallow embedding.